So it's so easy to use YouTube. So that's why many people would like to use YouTube. That's the reason behind.
Yeah, and there is actually another reason. I don't know how it's at Lund University, but at Delft University for education we use some content system. And you can only go into the content system when you're a member of the university. So if you want to share then your lectures with other people at other universities, you're unable because they cannot get into your content system. Yeah. However, if you use the YouTube, as Aki told me and lectured me how to use that, then you can spread all your lectures all over the world. And because moreover, you can not only go to YouTube, but you can also go to Bilibili.
Yeah, well, that's what we do also.
I had no clue what Bilibili was, but until Chinese students told me, oh yeah, we don't have YouTube, we have Bilibili. I said, okay, well, can you put me on Bilibili? No, I need Bilibili coins. I said, I don't have any Bilibili coins. But they had Bilibili coins, and now certainly the lectures on Multibody are on Bilibili.
So your lectures in the Bilibili and mine are out as well. And that's simply because we don't want to keep this as a secret information. This is a public information.
Absolutely.
So there's nothing to hide.
It's paid by public funds, so it's public. Right?
So whoever is interested, go ahead and follow.
I didn't check because
yeah, of course we don't know what's going on in this Bilibili because most of the writing is something that no idea.
Yeah.
No idea.
You see all kinds of strange symbols. Okay. First of all, sorry for all the technical mishap, but it seems to be working now. Thank you, Aki, for your technical assistance here. And it's a pleasure to be here again at Lapparanta University. I always feel very welcome here. It's a very nice place, and actually I would like to move here, especially with the weather today. So my name is Arend Schwab. I'm from Delft University of Technology. I recently retired officially, but I'm still employed there for 1.5 days a week. So I don't have many teaching obligations, but I do have some research projects which I'm able to finish. And my research is, well, you could say theoretical and applied mechanics. That's a very big umbrella. So you have to find your niche within that theoretical and applied mechanics. And I like dynamics always, and then particularly multi-body dynamics. I think Aki and we grew up in this community, or maybe the community grew through us, who knows. So we were the lucky guys that we were, when multi-body dynamics was at an infant stage, we joined, and then and it grew in time. As applications, I found then during a sabbatical year in the US some 20 years ago, as a nice application, I find bicycle dynamics interesting. And I'd like to share a little bit about this bicycle dynamics and control with you in the coming time. So the title of my lecture is Bicycle Dynamics, Control Theory and Applications. Are the lights good for the audience? Otherwise we maybe should
we
kill
can try
these.
to put them a bit off, but
Yeah.
that can be another risk factor.
No,
So
yeah.
I think it is there. So you know how to do it.
Okay.
Okay, so we again go in the wrong direction.
That's good.
Oh no, this
Yeah,
is
that's
great.
good. That's good. Not too much, otherwise people will fall asleep.
And another thing, just for your information, this goes to online participants too, is that Arend is an associate editor in the multi-body system dynamics, and your responsibility there is a vehicle dynamics.
Yes.
So if there's something you want to ask from vehicle dynamics, which covers, well, cars,
Trains.
mobile trains. Trains is like one particular branch within the vehicle dynamics. Well, whatever you feel that is in the field of vehicle dynamics, and maybe this is something that you're interested in.
Yeah.
Passenger cars, you can ask like, what's the best car? What's the best passenger car that I can select?
Or which e-scooter should I buy?
How to pass the annual check?
It's also no. I don't know. I can give advice on that. But let's see. Okay, I'm Schwab, biomechanical engineering, or just in some department, and then Delft University of Technology. So let's start with a movie. and say, why is it so interesting in bicycle dynamics? Well, this is an old movie, Jules de Vet, by Jacques Tati, 1949. It's about a postman who wants to rationalize and he wants to use a bicycle to do things quicker. And you see the bicycle move by itself. And of course, everybody thought, oh, that's a trick, right? Because movies always with tricks and so on. But actually, it's not a trick. And even when the bike goes around the corner by itself without any control, this is real. This is what bicycles can do. So bicycles have some internal intelligent model AI thing to keep upright. And then the big question is, how do they keep upright? What is that? Well, the question was, of course, very old already, but you can test that whole self-stability by yourself, by just taking a random bike, propel it on an open space, and you see it stays upright. But I always say, it's more than stable, it's sort of super stable, because when it's moving, you can hit it sideways, and then you see it oscillates, but the oscillation dies out. So that is clearly a very stable system, a dynamically stable system. And you may wonder, where do I notice these damped out oscillations? Well, in all cases where we have a mechanical system with some form of damping. But if you look at the bicycle, I mean, how much damping is going on? The speed is almost retaining, almost staying the same. Maybe something in the tires or in the joints, but well, let's see. The big question, where does this self-stability come from? Now, bicycle in itself is, of course, a very old contraption. It started around 1820 with this von Drijs, with this hobby horse, they called it, because it was a horse where you as a sort of a hobby you could move with your legs. And then there's a whole evolution, and you see first feet on the ground, and then somebody invented the idea of pedals on the front wheel. And why did he do that? Well, there is a certain speed by which you can use your leg, and then it's the end. I mean, your legs cannot go faster. And if you want to go faster, maybe you put pedals on, and then you can pedal a little bit. The distance is shorter. And then, of course, people are still not satisfied. They want to go faster. So what do? They make the wheel. They keep the pedals, but they make the wheel bigger. And so with every turn, you have more distance. So yeah, I will go faster. And you see, but there is a certain limit here. And it has to do, I think, with some physical limits which we have, the length of our leg. I mean, you cannot go further on, so what to do? And then there's a jump in evolution. Somebody came with the idea, well, why don't we use some gearing with a ratio, and then it's easier to put it on the back than on the front wheel, because of the steering, and now you split the two functions. Steering and propelling. But the funny thing is, it's so clearly in this picture that it's a evolutionary thing, because notice the big front wheel. Why do we have a big front? We don't need a big. And yes, of course. Then you see somebody, a smart guy, says, well, you actually don't need a big front wheel. And to demonstrate, he builds with a small front wheel. You missed the front. And then in the end, we slowly, you have this one, and then you see, well, there's a disadvantage because your arms have a certain length and you cannot reach to the handlebar, so what do? They do an extension here. And then there's a smart guy who says, well, this axis, we can also tilt it a little bit, and then we get this thing. So the handlebars are a bit more up front, you still have big wheels, you have space for your pedals. And this is actually the bike, well, it's called the bike you ride. Huh? Nothing changed since 1890 or something like that. So you would say, well, bicycle dynamics and control, it's not really a novel, very thrilling subject, right? Well, I hope to try to convince you it is actually, and it's very, very timely also from a societal point of view. By the way, you see that the people have one gene in their system, and I think everybody has that one gene, and it's called faster. I don't know what that is. Maybe we want to use time in a better way, or I have no clue. Okay, around that time, 1890, also mathematicians, of course, asked and mechanical guys, why is that the bike stays upright? And then Whipple in the UK and Carvalho in France, they almost simultaneously, like Newton and Leibniz, it's always that somewhere an idea around on the globe exists and people start thinking about it. And people have priority, but well, the priority is always difficult. Anyway, they come with a model and they like it so simple as possible, but still have all the ingredients you want to study. So rigid bodies, fixed rider, hands-free, everything's symmetric, knife-edge wheels, so point contact, no side slip, ideal rolling conditions, flat level road, no frictional propulsion. And on these assumptions you can make a model with 3 velocity degrees of freedom. Meaning you have a bike and the person is glued to the bike, and since we're not interested in control or in the bike itself, and then you can move back and forth, that's 1 degree of freedom. The bike can lean, that's the second one, and you can steer, that's the third one. But due to these wheel contacts, which in a nice way are called non-holonomic constraints, you have a bit of a difference between the configuration space, the coordinates, and the velocity space. Because the configuration space is of course bigger than 3 degrees, because you can put your bike anywhere on the plane at some heading, and that will not show up in the dynamics. In itself also a very interesting topic, but I cannot talk about it. Note that the system is energy conservative. No energy is going in or out. And that's already a bit in contradiction what we see, because we saw in the video that there was an oscillation and the oscillation died out. So we said that's damping. But in this model we have energy conservation. So you could say, I don't know if I'm going to see this whole stable thing, or maybe something else is going on. So what do we do? Well, this is your daily bread work, right? Your no problem. What do we do? Well, we just apply
People
Newton.
get bored easily because this is so easy. You know,
But
this is like daily living.
So you just do some Newtonian mechanics on the constrained system, and then you get 3 degrees. Your differential equations for your 3 degrees of freedom. There are second-order differential equations. And the lean angle, the phi, the lean, and the steering delta, and the forward speed, they are decoupled. So in a linear sense, we do linearized equations because we want to study stability. In a linearized sense, the lateral motions, which is the leaning and the steering, they couple the lateral motions, and the forward speed, which is the forward motion in a linear system, in this linear system, and it's straight ahead, not going in a circle, but riding straight in. These are just decoupled equations. So let's start with a simple one. Phi dot is 0, meaning that the forward speed is constant. Which makes sense, there's no propulsion or braking. And then the other one is a coupled second order system of leaning and steering, and there's some mass matrix, of course, there is some sort of damping, and that's linear in the forward speed. We find forward speed interesting because it's at 0 speed it falls over, but given some speed it stays upright, so we try to pull out that one parameter, that speed. You could also pull out the width of the wheelbase or the head angle, but for now we find that very interesting, the speed. So linear in the speed, this term. Then we have some stiffness term, and well, a large part is of course gravity, the thing falling over like an inverted pendulum. And then there's a part, the stiffness part, which has to do with v squared, and that has to do, if you go in circles, you have lateral forces, meaning you have, well, some people call it centrifugal or centripetal force. Centripetal is pointing inward, fugal is outward. You need a force to get it in let's call it centripetal forces. Anyway, this is the set of equations, and from this we can determine stability. Now I give you some numbers to show what we're talking about, in which ballpark are we. So the mass matrix is this. You see the term for the inertia for the lean, for the roll. The leaning is a lot higher than for steering. Your steering assembly, the inertia is very low, whereas you on the bike in rolling is very high. So there's a big difference here. Then here this magical sort of damping term, it's not asymmetric, it's not symmetric, there are zeros on it out of principle. Then gravity is just, well, again for leaning, this is just your mass, the whole bike of you, 80 kilograms, mass 20 kilograms, 100 kilograms at 1 meter, 100 kilograms at 1 meter. This, I don't know, has to do with the configuration here. And then this is this stiffness due to centrifugal forces. There are 2 zeros by principle there because leaning left or leaning right has no effect on that, if you can reason that out. And then 2 numbers, I don't know why they are like this, but the equations just tell. We assume exponential motion, we get the 4th order polynomial equation, and then as a function of speed, we're gonna calculate those 4 eigenvalues, which determine the eigenmotions. And we see here on the horizontal forward speed and on the vertical the eigenvalues. In blue we see the real part, and in red we see the imaginary part. The real part is either stable or unstable. At negative it's stable, positive it's unstable. And the imaginary part tells us there's an oscillation going. Well, at 0 speed we see 4 eigenvalues, 2 plus and 2 minus, and they are identical in magnitude. And these are just like an inverted pendulum falling over. And since we have 2 degrees of freedom, you have 2 modes. But when speed then increases, we see that these 2 roots form a conjugated pair. So from this moment on, oscillation emerges. And we have to look at the eigenvector to know what type of oscillation, what is moving. But the eigenvalue, the real part, goes down, 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 down. And here it crosses the axis. And then it has all negative values, this real part. So this oscillation from this moment on is stable. Then the other modes, if you look at the modes, this is like the caster wheel, the caster mode from the front. This is what we call capsize mode, and meaning you just fall over like a ship, slowly. And initially that's stable, and at higher speed becomes unstable. But with this configuration, you suddenly get from a certain speed a stable speed range. So this model already predicts that from a certain speed on, this initial oscillation just dies out, and the whole system works. So that's sort of magical. Let's check. So we have a computer model where we just multi-body model at slow speed. You see oscillation, and the angle of oscillation becomes, or displacement becomes larger and larger, and the thing falls over. So that's this unstable speed. This is actually what happens when you learn to ride a bike, right? It doesn't go so well, and the steering comes like and bang there. So what do you do then? Well, you just go faster. I mean, use your G's and you will go faster. If you go faster, you're also more stable. So if you go in the stable speed range, now if you hit the bike sideways, you see it oscillating, but the oscillation dies out. And that's gone. Exactly the same as we saw in the bicycle in the car park where we did the experiment. So yes, bicycles can be self-stable. Even a simple model explains. Yes.
In your last slide, you wrote there V dot is equal to 0, and now and the equation of motion was equal to 0 again because of that, I think. And now we are saying that if we going faster, it means that we have an acceleration. It will be steady or more stable. But these two sentences, I think that I feel it's opposite to each other. How it will equal to 0 when we have an acceleration?
Yeah. Okay. Good point. So what we study now is we study that we bring the bike in the upright position to a certain speed, and then we make a snapshot of that steady motion, the bike going at some steady forward speed, and then we say, okay, what happens now if we perturb that system, if we change a little bit the lean angle, if we change a little bit the steer angle, or if we change a little bit the forward speed. So that's the picture we take. And then the equations which govern that are these equations. So this is phi is this small change of the straight up head system. Delta is a small change of straight ahead cycling, and v is small change in velocity. So maybe I should have written here like delta v or something like that. Yeah, good point.
But hey, you realize that this is linearized equation of motion.
Yeah.
And this is what we are usually not discussing in our class. We always have this nonlinear equation of motion.
Oh yeah,
But when there's a nonlinear equation of motion, it behaves completely differently. Go ahead, Ari.
yeah, a good point, Aki. Why do we then still do linear equation? Well, because we if we want to say something about stability, we have to look at the system in some configuration and then say, okay, let's take a snapshot of the system and change it a little bit and see if that change goes away.
Yep.
And that's what we do, and that's what I'm doing here now.
This will be very. I'm even thinking, can you do that by using nonlinear equation
Yes.
and this time integration?
Yes.
You could kind of observe the same kind of behavior, but it's going to be a lot of work to do that.
No, yeah, yes, correct. It's a lot of work to do that. And there's one big disadvantage. You get probably only the most unstable mode is visual. The rest is totally not visible. All the other things are not visible because the dominant instability, then the largest instability will dominate the whole motion. So if you then have this nonlinear system, you perturb it a little bit and then bang, it will go in that one unstable mode. And what other modes are, and you have no clue. So therefore we like to do this linear stability analysis point by point. However, the pictures I showed here on the right, these are just full multi-body dynamics models where we just run them and make a nice animation and we see these large angles, even the front wheel was flipping. So that's the real multi-body part.
Yep.
So it's actually what you do always a combination. If you have a toolkit, there's not one screwdriver and one pliers which you have and say, okay, this is it. No way. Your toolkit is filled with all kinds of tools, right? So we need all kinds of tools to analyze our dynamical system. And one of them is linearized equations to look at stability.
Which we haven't discussed much. We have not discussed much. But this is one of the, in a real design problem, it becomes to be very handy to use it every now and then.
Excuse me. Like in your brain, the speed range that you introduced to us, like it was between, I believe, 0 to 10. So
Meters per second.
yeah, and you said that the most stable state is like between that point. And what I'm curious about is what happens afterward.
You mean if you get more speed?
Yeah.
If you go faster. Oh yeah, that's a limit case. So let's assume you go very fast. And then first I go back to the equation. I'm an equation man, right? Go back to the equation. So let's assume that V is very large. Yeah, very large compared with what? We always have to compare things. So in this case, we have here two terms. One term is a gravity term, and one other is a velocity, this velocity term. So if V becomes large, this becomes, well, this stays constant. So you can sort of cross out this term, right? So it's like cycling on in space. There's no gravity, right? Well, let's presume you can cycle in space in some way. Then what happens? Then now it becomes interesting because you have linear, the phi dot, the delta dot have linear v, and the phi have v squared. Now, if you now make this characteristic equation, this guy is out. And then you suddenly see you have lambda square, you have lambda times v, and you have v squared. And then you can do a scaling by dividing everything by v. And then suddenly the whole velocity is gone. Then the eigenvalue divided by the velocity is just the thing you want to calculate. Let's go to the figure. What do we get then? Then we get just 4 numbers, and it's all a linear with speed. So this line is coming to the origin, and it just progresses linearly. This line will go eventually to 0 in an asymptotic way. This line also will just progress in this linear sense, and this will also progress in this linear sense. So then it means from a stability point of view that the capsize mode will go away, of course, because capsize had to do with gravity and there is no gravity. And that the whole dynamics then just scales with this forward speed. So if the oscillation, if the speed is twice as large, the oscillation will be twice as large. But it's stable. Yeah. Good question. Nice. Okay, bicycle self-stability. Now we've shown by a very simple model that yes, bicycles can be self-stable. The big question is, why are they self-stable? Which ingredient makes them self-stable? Is it the pressure in the tire, or the nice yellow handlebar which you have, or the wheelbase, or because we have the wheels turning and it's like a gyro, or you have a slanted head angle, or it's the position of the rider on the bike. You like to understand the system, and for understanding this self-stability, I always call it automatic control, because it goes by itself. How does it work? That's a difficult question. So we want to know actually how does a bike balance itself, and we have no clue because we cannot say, hey bike, how do you balance? And then the bike will be very quiet, right? It will tell you nothing. Well, we could think, well, how do we balance the bike? Because if we are able to balance the bike, probably the bike, if it's self-stable, also will do something like that. Where optimizes, the bike is sort of an optimizer. But still, if I ask people in the audience, how do you balance a bike? They say, what do you say? How do you balance your bike?
It's completely intrinsic, I believe. Like you do it somehow subconsciously.
But suppose you want to get that subconscious to the conscious side. What does your conscience say? How do you do it?
How to balance the bicycle?
Yeah. What do you do to balance?
Just in, when we have the speed in the bicycle, we can balance it. We are not able to balance it when we are constant in the road. Just for the gyros effect.
Okay.
For turning
Other
back.
ideas?
I try to get some velocity and then don't use the what should I say, the
Steering?
yes, and then if it's go in a line, I feel it.
Okay.
Somehow I believe like we subconsciously we always try to keep our like center of gravity at one point. We don't want it to tilt so much in
Yeah.
order it to stay upright as much as possible.
Do we not like to tilt, or the bike?
Like I believe we
Okay, we don't like to tilt. Yeah, any other ideas?
By leaning the mass to one side or the other.
Yeah, so move your body relative to the bike and then sort of a balanced way. Yeah.
Yeah, one way is to turn the front wheel when the bike goes another direction, and then your body is or kind of goes in the other direction compared to the bike.
Okay. Well, anyway, I just wanted to show that there are all kind of different ideas on how does it go, and I also have difficulty in understanding what I'm doing on the bike when I balance. So, let's make a simpler problem. Let's say we want to balance a stick on our open hand, because that's kind of the equivalent that we have like a stick, this guy. And we want to balance that on our hand. Now we can do it. I'm old, but look, I can balance a stick on my hand. Now, to know what I do, here it's pretty easy because I need my hand here. I need my hand to move. So what I do is, if the stick falls to the right, I move my hand to the right. And if the stick falls to the left, I move my hand. So what I do is I put, as you say, with the center of mass, I try to put my hand all the time under the center of mass. And the center of mass is moving, so I have to move my hand, but in the end that sort of works. Okay. Now with that idea in mind, that is like balancing a stick on your open hand, how do we do it in the bike? So for the bike to balance, move the contact points, we have to move earth, right? It's not going to work. So apparently there's another system, and yes there is. We have a steering assembly. So if the bike is moving forward and we make a turn, then we move our contact points in a lateral sense. For instance, in this case the bike is moving forward, I steer to the left, and then my front wheel is accelerating to the left. So, and then my hind wheel will trail in that same direction, of course. But I have a mechanism here by which I can move my contact points to the left and right. And the mechanism is called my steering assembly. So apparently, only with the steering assembly, you should be able to balance. Forget well, you need not fall off the bike, but the whole system can apparently be balanced. However, there is an interesting thing already. So if you fall to the left, then you want your contact points underneath. So then you have to steer to the left to get upright. And that sounds like super crazy, because you would think, oh, if I fall to the left, I steer in the other direction. No way, that's totally going wrong. Double trouble, we call that. So it sounds very counterintuitive, like fall to the left, steer to the left, but actually it is the way to go. And to show that, we made a very simple machine from Lego Mindstorms. This is already very old and ancient, but the idea was you have Legos, you have motors to steer, to propel, you have a sensor, and you have a small computer. And then Joep Mutshuis built the thing as a master student, and actually he couldn't get it working. So I said, well, you just apply a steering to the fall. And then he said, yeah, how do I do that? Well, I said, there's a very simple law, steering to the fall. You have a steer motor, it's probably a DC, small DC motor. So you apply a voltage, that's the voltage which you apply to the DC motor is apparently the torque. That's at 0 speed, because there's not much steering going on. And then you measure the lean rate of the thing, and then you multiply it by 10 or minus 10 or 100 or minus 100 or whatever. You need some gain here, you need to have the sign right, otherwise you steer in the wrong direction. But you have to fiddle a little bit and it will work. And instead of going to work, he looked at me and said, yeah, but that's only one line of code in my controller. I said, yeah, okay, what's the problem? Because before he had, the angle and the speed and this, he had a very complex thing. So he went away, and after 5 minutes he returned with this thing. Totally autonomous, and the only control law is steer into the fall. It stays upright, so it works. And again, if you look at the video in slow motion, you see bike falls to the left and then steers to the left. Bike falls to the right and then steers to the right. And of course, because it's the only way how you can balance. So we observe it also in a real bike. Of course, comes the next question. Why does the bike do that? Does it have some deeper mechanism to do that? And there were actually 2 groups of people who had given that thought. 2, and one was, well, it's a gyroscopic effect of the front wheel. So the front wheel is like a big gyro wheel in space. It's rotating, and with gyros, it's always a 3-dimensional thing. So if you have a rotation about one axis, so that's the one axis, you then rotate it about the second axis, the vertical one, you get about the 4th axis, the horizontal, you get a torque. That's what you feel then, also. And if you look at the signs are correct. So if the wheel is turning like this, the angular momentum is in that direction. If you then steer it in that direction, then you have a change in angular momentum, and that makes it also this balancing act in the right direction. So yes, this steer into the fall can be done by gyroscope. However, if you check the number, I will come in a second. If you check the numbers, then the rotation speed is not so high, the inertia is not so high, and the torque is very little, but on the other hand, yeah, the steering assembly is also little, so who knows? Yeah.
At first, something is interesting catch from my eyes, and now I saw it again. Why this bicycle in previous video doesn't have chair? Is it had any effect on? No. Yes. on the center of mass?
Well, you could investigate that, of course, in your model. You could say, well, if the mass is lower and the center of mass is low, it changes the dynamics time scale a little bit, but that's all. Yeah, not so much. Yeah. Not so much. Good point. And there's nobody on it because out of ethical cases.
Since like we are paused, like can I ask a question
Sure.
about that number, that constant? How could you arrive on that, like that 8?
Oh, yeah, that's actually you at least need a PhD for that.
Too soon to ask
And
that
then
question.
after you got the PhD and you took all the classes, how do you derive that? Well, you just guess a number.
So you get the first PhD
You
and
just-
then you guess.
You just say, okay, let's start with 1. Oh, it's the wrong way around. Let's do -1. Oh yeah. Actually, nothing is happening. Oh, maybe it should be bigger. Yeah. And then 100. No, that's too big.
So like you
It's
have, like you came to that by trial and error,
Exactly.
and like another
And a
thing-
little bit intuition.
okay, and another thing that like in order to go back to being stable, like we have to like tilt it, not tilting, like somehow giving it a new direction somehow, like what you said, based on what you said. I don't know how to like say what I mean.
Steer into the
Yeah,
front,
steering it. And like, it might sound stupid, but I'm curious about it. Like, does it matter, the scale that we steer it? Like, there's a, like, somehow there should be an optimized thing for that. Like, if we go a little bit more than that or a little bit less than that, what would be the result? Like, are we going to be stable in, like, less amount of time, or it takes us more?
Good question. I have no idea. Actually, I'd like to invite you to just do the experiment. So I think you own a bike, right? So
I used to,
Yeah.
not here.
okay, well we can give you a bike. That's no problem. And then you just ride your bike, but don't grab onto the handlebars, because if you do that, you have no idea what you're doing, because you grab on. So the torque for steering is very low, so you will not feel it. However, if you take your open hands and you push against the handlebars, then you feel what you are doing. Because then, if you do like this, the force here is almost 0, and here you feel force, and then you feel, oh, I'm steering in this direction or in that direction, and I feel fast or high force, and that's a way to investigate this question which you do. And you could also take the model, of course, but I don't have the answer for you. Yeah. Okay, back to this self-stability. So it's stable because of gyro. Could be, number is little, but who knows. Other people say, no, it's this front wheel thing. It's the trail on the front wheel, and it's like a caster wheel in disguise, because here you have the steering axis, and that hits the ground somewhere here, and it hits the ground in front of the contact point. So the steering axis hits the ground here, and that the contact point is behind. So it's like this wheel on the chairs here, right? This swivel wheel. Yeah, wherever you go, it will always follow you, right? They say this is very important. And if you have the bike static and you lean it, you see that the steering falls due to the contact point being behind the axis, falls in that direction. Well, what's the answer? Well, the question was old, the ideas were old, and then Klein and Sommerfeld, I always say two half gods, they live somewhere up there. They are from the Klein bottle. Arnold Sommerfeld was 81 times nominated for the Nobel Prize. I was never nominated for the Nobel Prize. So they are really up there. And then Fritz Neuter, who was the assistant, had to do all the work. They were actually, their work was theory of gyroscopes, a German book.
So it's a book about theory of gyroscope.
Yeah. Well, not one book. It's 4 books, and it takes about this space in the literal sense on your bookshelf.
And the guy never won.
So maybe you need more books,
Maybe
or I don't know.
he had a hard time to explain himself clearly. So if it is that much pages to explain.
Well, to be honest, it's 3 books, and then the 4th book was with application. So then, in the fourth volume, it was about all these applications. And of course, if you're in gyros, you look around and you see a gyro everywhere you see gyros, right? So when they looked at the bike, they said, "Oh, there's a gyro." So they immediately dig up the literature. They looked at this Whipple paper, and they went into the derivation, and they showed from the stability analysis. Well, if you kill the gyroscopic effect, and it can never be self-stable, because the equations tell us, because this sign is this plus and that's the minus, and we kill it, it's gone.
And let me guess, this was this last book about the applications.
The applications, yeah.
Yes.
Last book. Yeah. However, my friend Jaap Meijert, who is my colleague on this work, he is the smart guy. He just followed the whole derivation, and he discovered 2 small sign errors. And mind you, the book is from 1910, and after that everybody copied the result, right? Until 2017.
That's that he never won.
Maybe, but we also know.
Okay, this is where we need to get back. That no one noticed that there was a problem. No
Yeah,
one
exactly.
noticed that there was a sign mistake.
It-
Because if they consider that these half-cut, like
The
I said,
half-cuts, yeah. They
so
are right.
the only thing that they were debating was that, are these guys better than the car or just below them?
Yeah, exactly.
But never check the word.
They never checked it. So 1910, between 1910 and 2017, finally 2017, Jaap Meijert discovered the 2 sign errors. He puts in the sign errors, and then it's not so clear anymore that if you kill the gyroscopic effect, that the thing is always unstable. So that's one debunked thing about this. Because everybody was always giving a reference to Klein and Sommerfeld. Oh yeah, the bike is self-stable because of the gyroscopic effect. Maybe not. However, Jones from I think it was from Cambridge, 1970, PhD. He was, I think, in chemistry, but he was interested in cycling, and he had some feeling, some intuition that the gyroscope is not so important. It's a small contribution. So to demonstrate that, he just built an apparatus where you kill the gyroscopic effect by just mounting a counter-rotating wheel next to the front wheel, and then it's in one frame, and then if one is rotating like this and the other one like that, then the netto angular momentum is 0, and then you say, well, look, mommy, I can even ride without hands. There's no problem. I have no problem controlling this bike, because self-stability and ease of control, he said, those are the 2 identical things, because I have no way to measure self-stability in some sense, but I can measure it very well when I'm on the bike and I feel how easily can I control it. So I said, I can ride it without hands, no problem. So the gyroscopic effect is probably not so important, because with and without, I feel not so much. Then he looks at the trail again, this picture trail where the contact point is behind. Well, he changed this trail such that he made the contact point in front of the steering axis, by putting that wheel forward. And then suddenly, it's a horrible bike. He cannot ride it without hands. With hands, it's very hard to control. And so he said, well, it must then be this whole, this trail thing. He comes into some analysis on a potential energy and gravitational systems and some energy thing, and then he comes with graphs and slopes and things, and the reasoning and says, yeah, look, if you kill it, then it's all negative and unstable and it shouldn't work. There's a small thing here. He only uses gravitational energy. And that means that the whole speed is not playing any role here. And gravitational energy is the same for a moving bike as for a steady bike. The whole dynamics doesn't come into play. And so, if we correct his reasoning with our dynamical system, then we see there's another term coming up. And then it's not so clear anymore. If you change that trail, that the stability is lost if you make it 0 or negative. So again, a lot of people follow Jones after the 1970s. He says, Klein and Sommerfeld, it's small, it's about the geometry of the steering assembly. That's the important thing. Both things are apparently not necessary. And we are looking for necessary conditions for self-stability. Sufficient and necessary. So what do? Well, we have our model. That's simple, right? We have our linearized equations. So this is the bike with our 3 degrees of freedom. So that's a manageable system, not too much degrees of freedom. However, the family of bikes is big. We have 25 bicycle parameters, like the wheelbase, the head angle, the trail, the mass of the rear wheel, the inertia, the mass of the front wheel inertia, what the body is combined. So this whole set of bicycle parameters, or this whole family of bicycle parameters, makes it that we have to look into the effect of these bicycle parameters on the stability. So we have to write down our characteristic equation, which you have to write in a form of functions which are in the forward speed. And then we have to apply the Ruth-Hurwitz stability criteria, which are actually 6 scalar equations which we get. But all these numbers, A, B, C, D, they are all a function of these 25 bicycle parameters. And then simultaneously, all these 6 equations have to be larger than 0. Now, if we even print the expressions for these equations, then I probably can fill all the walls of this university with a printout. So, and maybe we need build an extra building because we still have paper. So that's undoable. It's unmanageable to find out for which combination of parameters this will always be positive. So what do? We make the problem simpler. And we focus on the things we want to study. So we say, we make a 2-mass skate bicycle. And then we have only 8 bicycle parameters. So why skates? Because there's no gyroscopic effect. And we want to show that even without gyroscopic and even without trail, it can be self-stable. It's not a necessary condition. So we kill those. We kill it by making it on skates, by having the 0 trail, and then having a very simple sum max distribution. And that gives us 8 parameters. And now with the 8 parameters, I can write those equations on one piece of paper, and I can go stitch through my equations. And I can finally come to the conclusion that the position of the masses must be such that the front mass from the rear assembly in the mass and from the front assembly, they have some condition where they have to be. And then if it's here in this area, then the condition, there is no condition on the mass. If the front mass is in this area, then it's always self-stable. And if the front mass in this area and fits this condition, which has to do a little bit with the geometry, then it's still self-stable. So mass must be up front here and have some condition in relation to this in the geometry. And then if we look again at the eigenvalues, forward speed and the eigenvalues, we see this clear cutoff, and then after that speed, it's always self-stable. Stable without gyro or without trail. So that is interesting. So then we build it, right? So we build the machine, we go to the sports hall, and then we just give it a forward speed, and it stays upright. I didn't plug in, what is it, mouse? That's not too bad. It's okay.
So
And then-
that's your computer. What battery is that?
This is battery, that does.
Okay. All right.
So again, let me go back because it cut my story. So again, we give it just a forward speed and put it in this straight upward motion and see will it remain there. There's always a small perturbation, of course. It remains there. And then we do the second test, of course, we propel it, and then we're going to hit it sideways, and hopefully it will not fall, and it will come back again, and you see, yeah, there's oscillation and oscillation dies out. So self-stable, without gyro and without trail. And that was actually the topic of our publication in 2011, and we were able to publish that in Science. And we needed that. Because before that time, when I talked about bicycle dynamics, then people said, yeah, nice hobby. What is your work? I said, well, bicycle. No, your work, not your hobby. I said, no, that's our work. Oh man, that's too old. That's from the more than 100 years old. There's nothing new there. Are you not in AI or no, bicycles. This paper finally showed that, well, there's things still in this whole bicycle dynamics which are unclear, or where people thought it was because of some printing error, or they just.
Yeah, but that's nice. That's nice because you know the science is. You make a list of most appreciated genres. Science is it the first or second? That doesn't really matter, but it's really highly
Together with
appreciated.
nature there.
Yeah,
And then
so-
there's a whole big hole where there's nothing. So I think it's with an index of 57 or
Something like that.
60.
Something like that. So it's always a
And then
highly appreciated.
Body dynamics is
So
one-
that's done. Could be a bit lower.
A bit
Let's-
lower.
Let's say that is lower than science.
lower. Yeah,
I can say that with a high confidence.
me too. But we're doing our best, eh?
Yeah, of course.
Okay. Now we looked at the bike, right? The next step is, of course, what are we doing on a bike? Because we've seen that for regular bikes at slow speed it's unstable, and if you look outside, people do not fall. Well, some people fall, but they even can ride at low speed. So what is going on?
Sorry, that's
Yeah, that's my. I'll close it. I'll just put it up. Okay. And then close. Go away. Connection lost. Close. Yeah, it's gone. Thank you. So, riding control and handling. So the big question is, what do we do on the bike? How do we keep the bike upright? Two pictures. One of them is super famous. That's my daughter. She is super famous. I think she even popped up in talks in Japan where somebody used our slides or things and talked about bikes. So she's famous. And the other, I know this other guy, I think. Well, anyway, if you look at them, and if you observe what is going on, you see, well, you steer and you balance, but it's sort of unclear what you are doing. Is my upper body active? Am I doing a thing? Or am I steering and is the upper body passive because the bike is moving underneath? It's hard to distinguish what's going on. With respect to time, I skip this. So, how do we steer and balance? Now, that question was already old, and in the Netherlands there was already people looking at this bicycle balance, and it was not because they wanted to know how do people balance a bike, but they wanted to know, is it safe to ride a bike when you are intoxicated with vodka or by marijuana? And that's a typical Dutch question, right? So, and in the 70s, of course. And then the ethical committee said, well, we probably cannot put people intoxicated on a bike and let them ride. So they said, well, we understand, but we're still going to intoxicate them. But we built some simple contraption, a bicycle simulator, which leans and steers, and then we study their motions. And then, yes, of course, if they looked at the transfer functions, they saw that when you're intoxicated, that the gain rises enormously, so the steering becomes a lot wilder, and the delay in your control also increases enormously. And okay, and after that, I think by law, maybe now it is, but then it was still not enforced by law, but it was like an advice that you are not allowed to drive a bike, or it's better not to drive a bike. But I think now it's by law that you're not allowed to drive a bike intoxicated.
How is it here?
I don't know, you should.
Against the law.
I don't know. How is it here?
I think it's kind of case specific that if police can stop you and say that okay, you have too drunk, you take your bike and walk by it. But there is no official limit for this in Finland.
Okay. Good. But I trust that it's so easy to find the volunteers to this test, this intoxicated test.
We had absolutely no problem. We didn't have to give out gift cards or anything. There was a long line in the corridor. No problem. Then that's the bicycle side. So there was a societal need to investigate riding control. Then on the other side of the ocean in the US, there was also a societal need because a lot of more people were riding motorcycle and they were crashing. And then the big question from the Department of Transport was, well, is the vehicle inherent unsafe? Should we not ban all motorcycles from the American roads, which Americans are pretty good at that. They say, oh, that's allowed and that's not allowed. Right? So should we allow motorcycles or ban them? And then it started with David Weir, who made models, and later those models, again control models, were validated by experiments. After that, nothing much happened. By the way, the conclusion of David Weir was a regular motorcycle is safe to ride. We concluded it's not good to drive intoxicated. After that, nothing happened. Still, we were interested in this rider control, so what did we do? We put all these specific these are the active markers on the body and the bike. 31 markers, 100 frequency, 100 Hertz frequency, sample time 1 minute. One run is a lot of numbers, so we need some data reduction method to look what is going on. By the way, we were riding on a treadmill, of course, indoor. And then this was the whole setup, big treadmill, all this passive, this active marker system with the cameras, and then riding at various speeds and see what is going on. So here you see the video, and here you see the reconstruction of the motion. So nice way that you can visualize it also.
But here you move the ground.
Yeah, yeah. Does it matter? Is there a dynamical change if you don't? No, it is, and it's hard. I also had a very hard time understanding, but why does it work riding on a treadmill? And because you're not moving, and you have the idea that when you move, you gain stability due to your motion, but maybe not. Or
But you told us.
exactly.
Yeah.
And that works. I mean, if you steer and the treadmill is going underneath you, it moves the contact point sideways. So that system is there, and everything is rotating. But you can do a thought experiment. If you have a big oil tanker, you have a big deck, and then the oil tanker is in the harbor, and you just cycle from the bow to the stern. You cycle on the ship, and oh, that works. I can cycle. And let's suppose you go 20 kilometers per hour. Then you ask the captain of the ship, please put 20 kilometers per hour speed. And then he does that, and then thumbs up, there we go. And then when the ship is going in this direction, you cycle in that direction, 20 kilometers per hour. Right? So you're stationary to the inertial world, but you're cycling, and that works. I mean, you can cycle on an oil tanker. It's moving. Okay.
Warning disappeared.
Yeah, I can check.
So it's no longer there.
It's charging.
Okay, that's good. So can you put so let me take a look. No, the connection is back on, so it's okay. So only thing that disappeared was this camera from the US, from the OBS.
Maybe I don't know. I only know mechanics.
Okay, so that this is no longer connected. So
Oh.
can I take a look at your OBS?
Of course.
It's okay.
So is it back? So camera is back.
Yeah.
Okay, thank you.
We can see.
Thank you.
But the slides are not in presentation.
Yeah, there will be.
It's because
There
of
will be
delay,
soon.
I believe.
It will be soon.
Okay.
Like, before you start, like, a question. It might sound irrelevant, but the purpose of all those strings and everything, are they just for transmitting data or?
Yeah, so it's active markers. So to capture motion, you have two systems actually. You have the passive markers, so they're just reflective things, and then there's a whole array of cameras that look at these passive markers, and then they try to identify where was it in space. Sometimes markers get lost, the accuracy is a bit low because the markers have a definite size. There's also an active system where you put small markers, but they are cabled, so we need to tether the person in. But we need to do that anyway because for safety we need a harness here. So,
But
I
this
should
is
go
what
back
they
to.
do in a biomechanical simulation, because one of the things you have to have in a biomechanical simulation is a motion data.
Yeah.
And you can get it from the camera systems or you can get it from IMUs.
Yeah,
You
well,
need
the
to get
thing,
the data, you need to get the motion data.
actually, we need both. So the camera system is very good to finding the location in space. If you then need speed, then you do some numerical differentiation of the location. The IMUs are very good at getting rotational speeds. So actually we use both systems. For all the rotational speeds, we have IMUs on the system and accelerations and linear accelerations. And for the position in space, we use the motion capture system. Of course, you can say, oh, I use an IMU and then I integrate the speed, but then you get a drift slowly, and we want results as accurate as possible. So
Human
both
body is so complicated that you cannot just say, okay, I'm going to activate this and that muscle and I'm going to walk.
No.
That's not going to work out.
Yeah.
You know, the cables from here to here, they're so complicated.
I will talk in a second on that.
Okay.
So, okay, a lot of data, data reduction, and there we use the principal component analysis, which is a very powerful tool by which you actually you use again sort of eigenvalues of a system, and you look at the largest eigenvalues. But then you can do data reduction. Well, the conclusion was, and then you can extract most important motions, the largest motions, and then go to smaller motions. Largest motion was, of course, the lean and steer, and that's coupled. The analyzed the system showed that, of course. So you see steering and leaning, coupled motion. Then the yaw of the bike, the heading on the treadmill, it's an important one. Then pedaling, of course, and then this swaying of the other body, or bending also. You see also a bending going on, swaying. With the arms moving. Then there was knees going up and down, and then there were knees going left and right, in and out. And we found these interesting because we saw that also in the movie. All these motions are also a function of forward speed. So at various forward speed, we see different contributions. They make a different ranking. So here I showed horizontal is the forward speed, and vertical is the contribution. And then you see at low speed, the upper body is contributing not so much, but the knees are doing the work. And then as speed increases, knees go down and steering is most likely. So this showed us actually that most of the control, as long as we don't talk about very slow speed, is done by steering. And the upper body also goes away. That's a passive thing which is then going on. So, we noticed, oh, that is the control, because you could think, well, it's a control system, it's a multiple input, some MIMO in control system probably, and the inputs are steering and leaning of the upper body. But this already showed us that the upper body motions are probably passive and not active, and we do our balancing by steering. Well, two different speeds. Then the big question is, of course, everybody was totally happy with the science paper, and yes, scientifically okay, but what is the relevance to society? Because it's nice that you can write nice academic papers and be in a high-ranking journal, but what are we going to do with it? Are we going to get happy by this? Yes, we are happy, but are you happy? So what is the relevance to society of this research? Well, in the Netherlands there's a big relevance, because if we look at seriously injured, and you could also say death in traffic, but we have both graphs, but seriously injured is more interesting actually, I think. If you go look to the years, then cars become safer and safer. Bicycles become more unsafe, or cycling becomes more unsafe. So the total number of seriously injured increases every year in the Netherlands. Now, it has to do also with exposure, of course. More people keep cycling, people are getting older. But still, that's a problem. We always go for mission zero, right? We don't want any death or seriously injured in traffic. The numbers tell us differently. And if we look in detail, we see that 80% are elderly, and among those elderly, 75% are single vehicle accidents. So they do not get run over by a bus or a truck, they just fall over.
There's something wrong in the presentation mode, so it's stopped. So can you somehow ping the OBS?
I'm going to check.
So the OBS is not.
Oh.
Maybe you can hide it and put it back. This, I mean, just the window capture. Maybe you can hide that. Hide it there. Hide it and put it back. There, a little bit left.
Yeah.
There, hide it and put it back. So maybe that makes it activate. You know, this eye, and then put it back. Let me see. Yeah, I think it's coming back. So now it's okay.
Yeah, no, it's okay.
Now it's okay.
Yeah,
So it was something like, it was just the start of it.
thank you.
Ja, dus moest op mijn oren staan. Okay.
So, more people get injured. Among those are a lot of elderly, and it's single vehicle accidents. They just fall over. In this falling over, the stability of the bike plays a role, and the rider control plays a role. So we like to understand what is going on. Are the bikes unsafe? Are the people not fit to control them? What is going on? What can we do? Now, there has been an enormous rise in e-bikes, also here in Finland. And of course, everybody was saying, oh, it's these elderly on e-bikes. They're dangerous. They go too fast. Well, that's a nice scientific question. Is it unsafe for elderly? So we did a study with normal bikes and e-bikes with elderly going through a whole, in real traffic, measuring and seeing if they have extra attention. It turned out to be that actually it was okay. Actually, those elderly were unsafe when they didn't have an e-bike, because then they were going too slow and they were not keeping up with traffic, and then things happened. But when they use an e-bike, they go as fast as the rest of the cyclists, and that's actually good. So it was not the e-bikes, that was not the problem. Other applications in cycling which are relevant to society is sports engineering. Remember that one gene we have? Exactly. We want to go faster. We want to. I always beat Aki, right? Well, I sort of want to beat Aki always, right? And Aki wants to beat me. This challenge, you always want to be better, faster, and that's sports engineering. And engineering is where we can do some mechanical things, where we can contribute to sports, and we can do that. We can do it at optimal power distribution. We can do at the best bike for the guys. I can show you a number of examples. So for society, there are two applications: general public, health, other publications, sports. Let's go to the general public. If balance is a problem, why don't we do an active balance system on a bike? It's super simple. When you fall to the left, you steer to the left. You saw it on the Lego bike. We can make a Lego Mindstorm bike for a normal bike. So we can add sensors and motors to the steering assembly. We call that steer assist, and that actively stables the bike. So it's like a lane assist in your car. It nudges you in the right direction. Of course, you can override it. If it wants to steer left, you can just do right and you will fall. But it tells you a little bit what to do. There's a whole control scheme, not so interesting. Here we build a prototype where you see this motor, the steering motor, and some electronics. And then we show human control at unstable speed. no steer assist. There's a lot of steering going on, power spectral density of the steer rate when we have a human controller. Now we have the shared control of the steer assist. Theoretically, you're in a stable speed because it steers by itself. But what you do, we don't know. Well, this is what we know you do. That's the power spectral density of your steer rate. And we see that's a lot lower. There's a lot less going on. So it's apparently easier than to balance the control. And that's also what people say. Shimmy is another interesting thing. So this is this caster wheel from a shopping cart. And shimmy is this very rapid oscillation of this wheel. Everybody knows that. These are these caster wheels, contact point behind the steering axis, and again, the bicycle is a caster wheel in disguise, contact point behind the steering axis. On e-bikes, we have this problem. So she has hands off the handlebar, and look what happens. Well, this is not what you want. If you have a light touch on your handlebar, this sometimes happens. And of course, it has to do with the geometry of the bike, the mass distribution, and that changed because some have a front wheel hub motor, some have batteries on the back. Most of them have a stepped through frame, so it's rather compliant. And all these factors contribute. So what did she do? She investigated experimentally by putting accelerometers all over on the bike and all kinds of sensors to measure what are the motions. And it's difficult because it's a moving system, it's not in the lab. And then riding outside, recording all that data, finding that shimmy frequency, at what forward speed does that happen, and then doing a lot of test rides, and then looking at a whole bunch of different bikes we got, different geometries, and then this is forward speed, and this is real part of the eigenvalue. If it's green, it's stable. If it's white, it's unstable.
So stop.
Yeah.
So it seems that this live streaming is not willing to change the slides. Don't know why. It changes when you do that,
Okay.
but not automatic.
Really? What do I do then?
Nothing. I think it's okay. It will be okay momentarily.
No, it's okay. But
Yep, it's okay. Don't know why. That's okay. It
Okay.
is what it is.
Continue? Yeah, okay.
Yeah.
Sorry. So this is a very stable one, and this is a very unstable bike, right? And then we try to find out what design parameters do that. So we make that same bicycle model, but now we have to extend it with some flexibility in the frame and tires, and that the upper body can move relative to the bike. So we have to add just some more degrees of freedom to predict this whole shimmy behavior. And then this model is validated against the experiments, and for the model we built, of course, for the company, a user interface so that they can easily change frames and bikes and then calculate and see if it's stable or not, and then change the parameters. Oh, we do a little bit more of this and that, and oh, this bike has this type of tires, and so that's a very practical tool which they now use for designing bicycles, not in an evolutionary way, but in a scientific way, where they immediately from the drawing board can say, oh, it will not shimmy. And until now, that worked. Currently, we have done a number of experiments also on societal things, and currently we are working on the basin of attraction of cyclists fall. So this is the cyclist fall experiments in this year. We were able to do it in January and February during the COVID period, but it did work. So what are we testing? Well, we want to know about the lateral balance control of the rider bicycle system. What perturbations on steering can you still have, from which can you recover? So you're cycling and somebody hits your front assembly, somebody hits your handlebars. That happens, right? And then you can recover. Or if they hit it too hard, you cannot recover. But you can say, well, this change in the hitting in the handlebar can also be a pothole in the ground, or this disturbance, this perturbation on the system, it's a rather general perturbation. You can also see you get the hits on the frame sideways, but the steering assembly is very sensitive. So we wanted to know from what steering perturbations can you recover. Now, we worked a lot in rider control models, so we have some idea about rider control. We know what you use, your eyes and your hands, your haptics. We know a little bit about muscles and how they work. There's sensor signals and there's a delay and saturation. So we could build some system with sensors, some controller, some rider control, which is linear feedback with gain scheduling, some biomechanics for muscles, and then we can close the loop and we say, oh, this is the balance control, and then we put in a perturbation on steering, and then theoretically we can calculate, does it stay upright, right? So we can just make a big diagram, again where we have forward speed on the horizontal axis, and then on the vertical we have the disturbance on the handlebars, and I think it's now in radius per second, so it's an initial speed. It's like you give it an impulse, a hard hit. And then we see again, so we have the different type of cyclist. Let's say the naive old cyclist is able to recover from these disturbances. So everything out of this area he cannot recover from. So at low speed, he's unable. At high speed, he's unable. And then you have different kind of cyclists, and smart and older cyclists, they can recover, so they use a good control system. But young cyclists can even recover better. Well, this is a theoretical result which builds on a lot of assumptions, and we have no clue how true is this. So we want to do an experimental validation. And in my mind, I wanted to do it on the open road. I said we need a skyhook and we need to measure stuff, so that's it. And I live in the city of Rotterdam, which is a harbor city, and they have big cranes and mobile cranes. And I thought, well, we just order a mobile crane guy, and then we have a skyhook, and you put on a harness, and we measure the thing, and you let them cycle, and then the guy with the crane, he just follows the cyclist in as good as he can, and then we just hit the cyclist, and then he will fall over, but the crane will catch him. And should work. We have a lot of space in the harbor, and those crane guys, they are good. And then my boss said, no, it's too dangerous. I said, well, what's the danger, man? The guy follows, well, suppose something happens, he falls, and the guy cannot brake, he will right over, crush the cyclist.
I think this is how they move during these movies, these stuntmans.
Yes.
So I think it is a risky business.
Well, we can do it. No. Okay, that was plan A. Then I also had a plan B, of course. So the plan B was we go indoors, we do it again on a treadmill, and then we need some harness system. And luckily, we had a harness. There is a harness system at Delft for walking, and it's called Ryzen, and it's a linear system, so you can walk on a linear track from here to there, and sideways, something like this, and the harness moves with you. At the moment you fall, it freezes. So it's a number of cables which go through the harness. It's a very smart system, and it's used for walking. But we said, well, we put the treadmill in there, and then we can do the same. So we put the treadmill in there. We have the harness with the moving cables which freeze when you fall. Now we have to apply a perturbation on the steering. So we have cables on the side of the handlebars, 4 cables, because we want to do a left and a right, and we want to do a pure torque, so 2 forces either this or 2 forces either that. We have cables we can only pull, so we need 4 cables, 4 fast motors, and the motors, their task is to keep the cable taut at a low pretension, and then bang!
I don't know, there's something I need to ask. So the next class will get started 10:15, so soon we need to close. So soon we need to close, because we're supposed to close at roughly at 10 o'clock.
Okay.
So we can take a look at this example, I think.
Yeah, I'll do it. And then there are safety mats that indicate if you fall, you still do not hit the ground, but and there's a speed goat at high frequency, and then we have to measure the motions, the motion capture system, 13 cameras with passive markers. We have to measure the rate, so we have IMUs. We measure the EMG of the muscles, because we want to know when are they doing something. We have to order the perturbation. We have to we have to measure the force at the handlebars because we want to know what are we applying. All that system has to be synchronized. All these different systems have to be synchronized and work at approximately the same sample rate. Anyway, this is one of the results. As you can see, he's cycling on cycling on the treadmill. He's in this harness with these cables. There was a small perturbation going on, and you see that the twitch, but he's able to recover. So that first twitch is that he just gets pulled, and then he can come back. So he's stable. See all the cameras hanging here. You see some of the passive marks, EMG stuff, cables.
So we're gonna see some good crashes.
Yeah, like I was curious about like what's the extent of those twitches? Like, that's it.
Play again, please.
Yeah.
Do we have something like that in Loop?
No. So you would like to do that?
If you want to
but
do that,
intoxicating
come to
way.
Delft.
Okay, I will come. Because here we just have tractor.
I have a question.
I'll come to your question. Can I finish? You see him hanging in this harness. So he didn't touch the cushion side, of course. And what we also did, we connected him to the bike. Because in the beginning, in the test trial, the bike was disappearing and hitting the guy hanging. So we have a seat belt on our bike for safety, and we have straps to keep you on the pedals. Question?
Sometimes he really wants to rotate. This system can recognize he's falling or he wants to rotate.
The system recognizes that he is falling, and then it freezes. Then it freezes the 4 cables, and he stays in that position.
But he really wants to rotate.
Rotate?
So it's turning.
No problem. Because
It doesn't matter.
doesn't matter. There's a clear difference between a fall
Mhm.
and a human intent motion, unless he is able to move so quickly. But that's not gonna happen. And rotate. This is a hinge point. So it's really about the vertical motion. So this whole system makes it free to move in any direction, and then this point is free to do lateral and also vertical. And so in the 2 planar directions because of the 4 cables, and in the vertical direction. But the vertical direction is monitored. Well, the cable forces are even measured. It's a complex system, and then at a certain level it freezes. But we also have manual control for safety, of course. So it's either the system freezes or it is the operator who says, "Oh, hold it, this is wrong."
So what was that question? So can you please ask again?
The joints for the wheels are
Wheels?
being
Yeah.
prepared. The joints between the whole frame and the wheels.
So you mean this treadmill? That's what you're asking.
No,
Related to
about
treadmill?
the bicycle.
Bicycle.
Yeah.
So how is the joint in a bicycle?
Just the joints between the wheel and the frame.
Wheel and the frame. Well, those are bearings. So those
It
are
should
usually
be.
the ball bearings
And
without gates. Without the gates. Simple bearing system, which can be considered as a.
and it doesn't move like this, yeah?
No. If the
No,
pipe is okay.
it's just one the rotational,
Yeah.
1 degree free.
No,
And then this is
soon we need to close because
Yeah.
guys need to go to some place else.
exactly. So here on the horizontal axis you have the desired pull force, and then the size of the bullets tell you how many pulls there were on this force, and then on the vertical it's a recovery or a fall. It's very on or off, of course. It's either you fall or you recover, but you see sometimes you fall at this force and sometimes you recover. And well, there are all kind of other influences. Still you can fit some exponential linear regression curve here, and then you can determine what is the 50% chance. This is a 100% chance you will fall at this force level. This is a 0% of the fall. chance, and then somewhere in between is like say a 50% chance of fall, and that's around the 60 Newton applied. And we do that for a number of participants. Look at all the people. So the oldest person was 76. Found very, I had a very bad feeling pulling the guy off the bike, but well, yeah, the instructions is also contradictory. Do your best, but we're going to pull you off. Yeah, what am I going to do? I'm going to do my best, and then you fall. Yeah, that's very discouraging. Yeah, but still, we have to continue. We did about 20 of these tests. That's about it for the societal thing. We also work a lot in sports engineering. There's no time left, unfortunately. I do want to say that we were part of the team that built the Tokyo 2020 track bicycle, the new one, and we won 3 gold medals, 1 silver and 2 bronze, only in track cycling with that bike. No, not with the bike. With the cyclists, of course, but we also were able to work on the bike. Okay, thank you.
To be continued.
To be continued.
Nice.
If you have a few questions, like, can we ask them or should we wait?
Well, what we can do is that I think what we can close the streaming.
Yes.
And if you have some
And then we
additional
can
comments, we can
discuss.
stay here. You can ask. No, we never have a time to discuss about other vehicles than bicycles. But we'll see. Maybe we have a opportunity to discuss those other vehicles too. Trains are very interesting, but they are really special cases. Trains, you know, rail and the wheel. This connection is very unique.
Yeah, and I was in the lucky circumstance that Delft was Joost Kalker, who was the guru together with K.L. Johnson in the UK on the wheel-rail contact. It was my personal friend. And his wife is still alive. She's still a personal friend. I did not really understand all his mathematical work, but he always said, well, that doesn't matter. He's a very nice guy.
Okay, so I'm gonna close the streaming.
Yeah, please. Sure, I do it or you?
You can do it there too, but I close it here.